In this video, we are going to begin our discussion of section 3.1. This is going to be a section of applications that come from DiffyQs. So the first thing that we're going to do, you guys have seen this before, but not in this form. You have seen where we're going to get what the equation will look like. I think you've seen it probably in your Algebra 2, College Algebra, Pre-Calc 1 courses, wherever you might have taken an algebra course. All right, so this first setup, this rate that we can look at, is both based on growth and decay. It could be a population, it could be an element, but we have found that a lot of things in nature grow, like let's say population of some colony, I don't know, population of colony, the rate at which the population grows is actually dependent on how big the population is, right? So if the population is small, it's not going to grow very big, but if I have hundreds of thousands of people, the growth rate is larger. So what we're saying here is that the growth rate, and this X, be careful, this is our output. So if it bothers you, put a Y there. But the output, the rate, dx dt, according to time, is directly proportional to the population itself, which is our X, not time. X is population. So there is some kind of multiple. Since it's directly related, we can find some K given a measurement. We do this quite a bit, that if I had a petri dish of bacteria and it grows, and I'd get a measurement at time 0 and I'd get a measurement at 1 minute, and we could use that to find that K. So that K is there. Now, this is not a model of how much material would be there or how much population would be there. This is just the growth rate. So we're going to use this to come up with a model. We're going to use it through an example. Okay, the population of a community is known to increase at a rate proportional to the number of people present at time t. All right, that's exactly what they're saying. So I'm going to do dp dt. We're going to put it over here to the left a little bit because we're going to work down and we're going to need the right column. Right, so this is equal to some kp, some population. It grows proportionate or directly proportionate to its population. All right, so if you take this and we manipulate it, this is actually, we could go about a couple different ways. I don't know why I prefer first order linear over separable, but I just do. But this is separable as well. So I have that. This tells me that mu of x, because it's first order linear, is e to the integral of negative kp dt. Or no p though, right? Because we don't want the output variable, dt. All right, so that means that my mu is just e to the negative kt. Okay, I know that when I multiply my diffie which is right above here, by that, by mu, I get the quotient rule, ddt, of e to the negative kt times p. That's our output. Remember, first order linear, it always works that way. And then on this right side, we would multiply also, I'm going to put it here just for note's sake. We also multiply by that e to the negative kt. All right, the whole reason for this was that I can integrate. So if I integrate both sides now, I get e to the negative kt times p. And then be careful with the 0 on the right. We get a c1. All right, so there's our c1. And it's going to end up being, we'll see. Okay, so I have that. Now I can solve for this p, and I'm going to go ahead and put p of t, its variable. And it's going to be c1 times e to the positive kt. Okay. Now they gave us the population at the beginning, and it's kind of hidden here. If the initial population is p naught, so I do grab something from that. I know p of 0 is p naught, so I'm going to use that to find my c. It's going to turn out nice and easy. Okay, I get p naught equals c e to the 0, so that means c is equal to p naught, which means my function is p of t. Oops, p of t equals p naught e to the kt. Now notice, okay, p naught in this case is not considered a variable. It's a parameter. That's just our initial population. What we're going to do now is they want to know, it said, if initial population is tripled in 3 years, how long will it take to double and then quadruple? Okay, so first things first is I'm going to figure out how long it's going to take to get me, it's tripled in 3 years. We're going to use this. So what this says is, okay, P of 3 is going to be 3 times P naught. I know the 3 there is kind of confusing, but the 3 in the parentheses is time, and then the 3 times P naught is the triple. So I'm going to use the equation that we had down here. 3 times P naught, that's our output, equals P naught E to the 3K. We plugged in T there. Notice this happens, this is why this problem works out, that P naught on both sides, so I can just divide by it and get it to go away. So I've E to the 3K. This is an ln problem. So if I take the ln on both sides, I get ln of 3 equals 3K, which tells me I'm going to do it here for room's sake. K is ln of 3 over 3. Those threes do not cancel. We can't just have an ln by itself. Doesn't make sense. So please don't try to do that. So we have this new equation now. P of t equals P naught E. And then this is going to go here. ln of 3 over 3 t. So it's not pretty, but that's okay. We could get a decimal, but I kind of like to leave it exact until I get to where I need to go. They want to know. So here's our equation. I'm going to go ahead and highlight this so I don't lose it. I have to try to find it if I look back up. All right. They want to know how long is it going to take to triple? So, or they told us to triple. How long is it going to take to double? So I'm going to have 2 P naught equals P naught E to the ln of 3 over 3t. So the P naughts go away. So I'm rewriting now without those. Right? Again, I've e to power equals a number. This is an ln problem. I get ln of 2 equals, and then we're going to ln of 3 over 3 times t. The e's gone. So this tells me, it gives me a t. I'm going to go right here to do this because I want a little bit more room because we had to do quadruple. This is going to end up being, I would multiply by its reciprocal. So I'm going to get 3 ln of 2 over ln of 3. Right? And then now I can use my calculator to get that approximation, if I can get that thing to come up. All right, so we get 3 ln of 2 divided by ln of 3. And I got approximately 1.889. That's fine. And then I don't remember if they said, what did they say, years? Reset a rate proportion to the number of people present time t, 3 years. Yeah. So it would take that many years to double. All right, so that's the double one. And then we're going to do the quadruple, which is times 4. Not a lot's going to change. We can kind of look here maybe at the equation above and try to track it to find where it's going to end up being. Or you could follow it and divide by P naught. ln of 3 over 3 times t. So I get ln of 4 equals the ln of 3 over 3 t. Some of you guys probably could have just wrote down the answer using a pattern. So this is going to get me 3 ln of 4 over ln of 3. And then that shouldn't be approximate there. That's an exact. So this is equal. Now I get my approximate. So I'm going to copy and paste because I can just change the 2 on top to a 4. And I get 3.79 years. All right. So that's how this model works. You guys have, I think, have seen hopefully this at some point. That thing is usually taught in pre-calc 1. They don't usually start with the diffie-q, obviously, because you wouldn't know what a derivative was and you couldn't do any of that. But usually they say, okay, initial population e to the kt. And then you have to solve for they give you the initial or they give you K or T like they did here, and you got to solve going backwards. It just didn't involve any of the calculus at the beginning, which was literally only right there. Everything else is algebra. All right, we're going to do another problem like this in this video. Now we're going to talk about population of bacteria. So on this next page, the population of bacteria in a culture grows at a rate proportional to the number of bacteria present at time t. So this phrase right here, grows at a rate proportional to the number of bacteria, right? Or the culture population, that tells me to use this model. So I'm gonna write down the model, D, and then what are we gonna call this? Is it population? Yeah, so dp dt is directly proportional to the population. Now, you don't need to rework this thing out again. You know it's going to work out to this on an exam. Please work it out. I want to see it. So I'll try to remember to put that in there, but I want to see it. But please do the derivative, the diffq part of this problem for a test problem if it pops up. I'll make sure the directions say to derive it. All right, so we're going to get P naught e to the negative kt. It wasn't negative, it was positive. Doubted myself there for a minute. There we go. All right, so we're just going to use that here. Okay, they say after 3 hours, so let's write that down. After 3 hours, it observed that 400 bacteria are present. So we have that. And then they have also after 10 hours, they have that 2,000 are present. So notice in this problem, how it's different is they gave us 2 data points. Anytime I see multiple data points, I'm thinking some kind of system probably. So I'm going to take my P equation and maybe create a system out of this. I'm going to get 400 equals, and we keep our P naught. I don't know what the initial population is. And then we do know time was 3. All right, we're going to do the same thing for the second equation. 2,000 is the bacteria growth or the result. Then we're going to P naught, still don't know what that is, to the 10K. All right, so we have a system. This isn't a linear system, so I can't use my calculator, unfortunately. So what we can do, usually what I try to do here is plug one into the other or get them both set to the same variable. We can set them both to the same variable, 400e to the negative 3k equals P naught. And I know a second ago I said P naught's not a variable. It's a parameter, but if I set up a system with just k and P naught, then P naught becomes a variable. In our problem, it's a parameter, it's a population. But in this little bit we're doing right now, it's considered a variable. All right, so since those two things are equal to P naught, I can set them equal to each other. Okay, so I have that. Now notice the e's, I can put them on one side. So let's go ahead and do this. Okay, I get e. I'm gonna divide both sides by e to the negative 10. Okay, e to the negative 10, or you can think multiply by positive or multiply by e to the 10k if you want to do that. And also, since I'm going to do that, I'm going to go ahead and divide also by 400 just to get the number on that side. Okay, so on the left side, I'm just going to have e to the 7k, negative 3 minus negative 10, if you want to think about it that way. And then on the right, this is gone, that's gone, and then we get a 5. All right, so that's just a logarithm. So I get 7k equals ln of 5, which means k is equal to 1/7 ln of 5, or you could put the whole ln of 5 over 7, same thing. All right, so that gives me my equation. P of t is equal to P naught e to the 1/7 ln of 5 t. So notice we still don't know what P naught is. But now, since we solved for k, I can actually just plug in one of my values to solve for it. So I have, let's do P of, what do we have here? 3 is 400. So we'll plug it in, 400 equals, we don't have P naught, but I have E, and then I have to the 1/7 ln of 5 times 3. Okay. That's just a number up there. So I know that P naught is equal to, I can just divide by that if you'd like. I'm going to go ahead and just make the power negative. So it's 400 e to the negative 3 times 1/7 ln of 5. I put that 3 on the front, made it negative to move it over. So whatever that is going to be my initial population. So let's plug that in. I got 400 e, find it, e to the negative 3 times 1 divided by 7 ln of 5. Okay, and I got P naught to be roughly 200.6788. Right, so that's our initial population. I don't know what they grow it in. It just says bacteria. So there's that much bacteria. I spelled it right. Yep, texting's ruined my spelling. So let's make sure we answered the question that was asked. It said, what was the initial bacteria? It would be that much. So we could try this now. Okay, P of T is equal to, and I'm going to put this in parentheses so it's not crazy looking. I got E, and then it's going to be 1/7 ln of 5 times T. Now, if I plug this in, I should be able to check my table. Now, it might be slightly off because we rounded that 200.6788. But to check, what I'm going to do is just go up to y equals, and I'm going to plug this in, 200.6788. Close that thing. E to the 1/7 ln of 5 times, and then we would have our variable. I'm going to go ahead and close that again, and then x. All right, so now what I do is I can go to the table, or I could just go back to the screen if I wanted to, and go to vars, over to yvars, functions, pick my function, and now I can plug in things. If I plug in 3, I should get close to 400. It might be off. Yeah, slightly off just because we rounded. If we wouldn't have rounded, if we were able to do that, then it would have worked out. Now, this says if I plug in 10, then I should get the other number, which is 2000. So we are good. We can check these things with the data given to us. All right, so the question was not for the equation. The question was for the bacteria. So again, the diffie-Q stuff really is just the very beginning of changing the rate, the proportional rate that we can observe in nature. We can solve that diffie-Q to come up with this model. So this is used often for growth, decay. We're about to use it in the next videos with carbon dating, half-life type stuff. So there you go.